Hello, everyone. Welcome to today's live broadcast, Advancing Chiral Separations. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event, which is part of our Editors Series. We're delighted to bring you this educational web seminar presented by LCGC and sponsored by Regis Technologies, a trusted partner to expedite drugs to market for 60 years. They offer cGMP and non-GMP synthesis and separations services to the pharmaceutical, biotechnology, and other industries worldwide. With over 30 years of manufacturing unique chiral stationary phases and nearly 10 years of offering SFC separations services, they are an expert resource for chiral separations. Browse Regis's full chromatography catalog for chiral columns, unique tools such as their immobilized artificial membrane columns, GC derivatization reagents, and more. For more information, please visit registech.com. We have a few housekeeping announcements before we get started. First, the webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, which you can find on the left-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation, please click on the question mark help widget in the dock at the bottom of your window. I would now like to introduce today's speakers. We're very pleased to be joined today by Zach Breitbach. Zach Breitbach received his PhD in analytical chemistry from the University of Texas at Arlington under the direction of Professor Daniel Armstrong in 2010. He continued his career at UTA serving as a research scientist where he helped develop new chiral stationary phases for HPLC, SFC, and GC. He also served as a consultant to AZIP LLC regarding new chemical separation media focused on HILIC and chiral HPLC separations. Currently, Zach is a senior scientist at Abbvie. He has published approximately 60 peer-reviewed research manuscripts, holds 3 patents, and has presented work at numerous research conferences. Before I turn it over to Zach, we have a brief polling question for all of you in the audience. Please click directly on your screen to submit your answer. And the question is, what is your greatest struggle in your lab? Time, complexity of samples, number of samples, choosing the right column, or budget or organizational resources. So once again, you can click directly on your screen to answer. What's your greatest struggle in your lab? Time, sample complexity, number of samples, choosing the right column, or resources. Give me one more moment there. All right, let's pull up the results. Ooh, looks like we're pretty evenly split among the 4 of the answers: time, sample complexity, choosing the right column, and budget and organizational resources. Not too many people worried about the number of samples per se. All right. Well, thank you so much for answering that polling question. We'll now get started. Zach, you have the floor.
Thank you, Laura, and thank you for the kind introduction. Thank you to everyone who's joining us online. As was mentioned today, my talk will be concerning recent advances in chiral separation technologies. And generally, I'd like to just give an overview of what new technologies are available and give a detailed presentation of what new technologies are on the horizon. I really think that some of the new technologies that are on the horizon and may be coming out in the near future might help with some of those struggles that were just mentioned in the polling questions, such as choosing the right column or the amount of time that is required to acquire method development for a chiral separation. So with that being said, before I get into any of the new technology, I thought I would take a few slides to just go over a little bit of the background and the importance of chiral separations. One thing I always like to start with is this article from 2003 in C&E News. This was an article where they listed all the most beautiful chemistry experiments of all time. And in that article, atop the list at number 1, the most beautiful chemistry experiment of all time, was the manual separation of enantiomers by Louis Pasteur as he separated enantiomers of sodium ammonium tartrate in 1848. At the time, Pasteur didn't realize he was separating enantiomers, just that they were 2 different crystal forms, but it was quite interesting, and obviously it was thought to be quite impressive. It did require a little luck, but quite impressive as it came in to be the most beautiful chemistry experiment of all time. And it shows that we have this interest with chirality and chiral separations and has fascinated many of us for over 100 years. Now let's fast forward about 150 years up to current time and what we're looking at now when it comes to chiral separation technologies. Loosely looking at this cover from last year, this cover issue from Analytical Chemistry last year, you can see in the middle of the cover there's a chiral separation. It may be hard to see on your screen, but basically it shows a chiral separation that occurs in about 5 seconds. So what I'll do throughout this talk is discuss some of the technologies that have come to the forefront recently, which allow us to go from difficult types of separations and chiral separations that was very difficult 10 or 20 years ago to something that can be done much more easily and quickly today. Now just one more background slide in terms of chirality. Think about chirality in drugs. This is oftentimes the most important facet of chirality and where we need to perform chiral separations. Of course, in 1992, the FDA released a policy statement on stereoisomers in drugs and how to treat them. And in the 2000s, we see that approximately 3/4 or 80% of approved drugs are chiral, and about 70% of them are single enantiomers. So, of course, chiral separations is hugely important in drug design. Of course, this is of big importance because the potential effects of other enantiomers impurities. You could have decreased efficiency or efficacy of a drug if you had the enantiomeric impurity present in the drug. You could have side effects or unintended effects, and of course, toxic effects. One of the most commonly used examples is the administering of thalidomide as a racemate in the 60s as an antiemetic for pregnant women. Of course, all the many babies that were born from women who took thalidomide were born with terrible defects, as you can see in the picture in the upper right corner of this slide. Another interesting thing when it turns to chirality in drugs, if you look at the drug methamphetamine, which most of us have a bad connotation with as a drug, an illicit drug, which causes euphoria and terrible addiction. But in fact, you might be interested to know that you can go to your pharmacy and buy methamphetamine over the counter if you buy the non-addictive enantiomer, which is sold in Vicks Vapor Inhaler and other vasoconstrictors. And the last point on this slide is just to point out that chromatography, and particularly HPLC, is the most commonly used method for separating enantiomers. So that's why we'll focus this talk almost entirely on HPLC and partially on SFC separation of enantiomers. So that's all for the background. Now let's look at what can we do to improve chiral separations. Oh, for the past 30 years or so, chiral HPLC columns have been available. So that's quite a long time. So the question is, what can we do to improve these chiral separations? Well, there's really 3 main foci, and they're listed on this slide, of how we can improve chiral separation technologies. The first means to improve a chiral separation technology is to improve the selectivity or the stability of the chiral stationary phase. And this has been done through the introduction of new chiral selectors or the immobilization of the chiral selector or increasing the stability of the immobilization of the chiral selector. And really, looking at new chiral selectors was about the focus of the last 20 or 25 years in improving chiral separations. But more recently, we've moved into an area where there are different means and different strings we can pull on to improve chiral separation technologies. And that's the other 2 foci here. The second one is efficiency. Can we make more efficient chiral columns? And I'll go into this in detail in my talk. And that can be done by using sub-2 micron silica, narrow particle size distribution sub-2 micron silica or UHPLC silica, and through the use of superficially porous particles. And I'll explain all this in detail throughout my talk. And lastly, the third way you can improve chiral separations is through speed. How can we screen chiral columns as fast as possible, and can we make our chiral separations even faster and faster? And I think some of the new technologies I'll describe in this talk will show that that can be done. On this slide, I've listed the main classes of chiral selectors and chiral stationary phases that are used today. They are polysaccharide-based chiral selectors, starting at the top, macrocyclic glycopeptide chiral selectors, pi complex-based chiral selectors, cyclic oligosaccharides, and then there's a few other random chiral selectors that are used infrequently out there. What I want to do on this slide is just show some of the advances in each of these areas that have increased either the selectivity or the stability of each of these types of chiral stationary phases and these recent advances. Polysaccharides have recently seen some new selectors come on the market. In fact, there's a new chloral methyl substituted amylose-based chiral selector that was just launched earlier this year, and it seems to be a continuous research area where we're looking for new, more selective chiral selectors of polysaccharides. We've also seen that over the last 5 to 10 years, different bonding and immobilization strategies for polysaccharides have really increased the robustness of polysaccharide-based chiral columns when compared to the original coated polysaccharide-based columns. For macrocyclic glycopeptide-based chiral station phases, there have been a few new chiral selectors studied. Boromycin was one, and dalbavancin was another chiral selector, but neither of these chiral selectors were really approved to go to the market. For the pi complex-based chiral selectors, we saw an increased stability with new stably linked Welko-based chiral stationary phases. And for cyclic oligosaccharides, in the last 10 years, there was a launch of a new cyclofructan-based line of chiral selectors, one of which is exceptionally selective for chiral primary means. This is a cyclofructan derivatized with isopropyl groups. And finally, in the others category, we saw the launch of some new quinine and quinidine derivatives, which are exceptional selectors for chiral acids. So those are really the advances in new selectivity. As I mentioned earlier, new selective chiral selectors has kind of been studied for 2.5 decades. Now we're moving into a realm where we want to increase the speed of our separations and the speed of finding the right chiral stationary phase. And that's what I've addressed on the next few slides. Let's not look on at the figure on the right. Just look at the words on the left. The words on the left generally describe how chiral separation methods are developed in most labs today. Really, finding a chiral separation method is a brute force screening method in which we want to screen as many columns as we can in the shortest period of time. This is most commonly done with an HPLC with switching units where you might hook up 6 to 12 columns on your HPLC or SFC and make an injection on one column, and then the switching valve will switch to the next column, and you'll try the separation on the next column so that you can screen as many columns in a short period of time as possible, and then find out which column is most selective for your chiral analyte. Of course, as I mentioned, SFC is often used for this type of separations, and fast gradients are often applied. And if you have the ability to couple your separations with mass spec, you can also speed up your analysis. If you have multiple samples, you can put different chiral analytes in one sample vial and inject them at once and do peak tracking using mass spec. Now, in addition to this type of column-by-column screening, brute force screening, there are other configurations where you can screen parallel columns at once, and that's what's shown in the diagram to the right. I won't go into any detail on the diagram on the right, but just so you know that there are parallel column screening units out there that can be used. For example, the screening unit described in the figure to the right in A shows basically a unit which has 8 pumps, 8 injectors, and 8 detectors on it so that you can run 8 columns all in parallel. It's essentially like having 8 HPLCs running at once. Column dissections in B, C, and D in this figure show systems where you share a single pump, but you have dedicated detectors to each line, and they each have their advantages and disadvantages, whether or not you have back pressure regulators on each column, whether or not you have split injection across the columns. But each of these configurations allows you to screen multiple columns, perhaps up to 8 columns, in one given injection at one time. So this really helps speed up the screening process. What I've shown on this slide, and I won't go into detail, there's a lot shown here, but what I've shown is basically the output of if you were to use, say, an 8-column parallel screening unit. In this situation, we actually show an example where the 8 columns, channels 1 through 8, are actually all identical amylose-based chiral stationary phases, but the way this parallel screening unit was used was to look at different conditions for asymmetric synthetic reactions. So looking at this plot of all the chromatograms that you get simultaneously, you can see very easily which chromatogram or which reaction that you're monitoring gave the highest enantiomeric access. In this case, you can see in channel 5, in row 9, you can see you have something with that was nearly racemic. So you can see that that gives you maybe a catalyst, a chiral catalyst that worked most effectively. In chiral screening, you might have a situation where channels 1 through 8 are all different chiral stationary phases, and you're able to inject on them and see visually and very easily which chiral phase gave you the best separation for your chiral compound. Another technology that's useful for high-throughput chiral analysis is called MISR. MISR stands for multiple injections in a single experimental run, and basically utilizes injector programming. So you program your injector to make multiple injections within a single chromatographic run, and the main advantage of this is that you can see visually all your chromatograms in one run, and all your data is accumulated in a single run. So if you need to export your data into Excel, everything is right there, and you can very easily see if you're, for example, monitoring different reactions or monitoring racemization of a drug. You can see the different peaks changing as they go throughout the chromatogram. And you can see an example of a Miser chromatogram on the bottom of this slide where different enantiomeric excess ratios of Troger's base were injected in a single run, and you can see in each injection you can get a different enantiomeric excess. Again, this is in a single run, so the data analysis is a little simpler that way. Now, the remaining portions of my talk, I'll discuss new chiral stationary phases which have increased efficiency, since this is currently the focus of most of the new column technology that I'm seeing being researched on. On this slide, I've just looked at the state-of-the-art of efficiencies of chiral columns and chiral separations. For the last 20 years or so, 5 micron to 10 micron fully porous particle-based chiral phases have been the state-of-the-art. Only recently did we see, with polysaccharide-based phases and pi complex-based phases, that 3 micron and 3.5 micron fully porous particles are commercially available. But with the 5 micron based chiral stationary phases, you'll see that 30,000, 40,000, 50,000 plates per meter was generally acceptable over the last 20 years. However, we see in other modes of HPLC, they've progressed much further to have efficiencies greater than 250,000 plates per meter. And this is what I'm talking about, doing your reverse phase achiral separations or HILIC separations, which must have much higher efficiency than the chiral separations you're used to. And the reason that this happens is because chiral separations are inherently low efficiency, and that's because they have slower adsorption-desorption kinetics for the chiral analyte coming on and off the chiral stationary phase, because there's strong interactions at play there. And you can see this comparison on the 3 Van Dempter curves on this slide, where you have a reverse phase separation Van Dempter in green, a HILIC separation in black or purple, and a chiral Van Dempter curve shown in red. And you can see, indicated by the purple arrows, the increase in the slope of those Van Dempter curves as you go from reverse phase to HILIC to chiral. And that's because, as I said, the adsorption-desorption kinetics are quite slow for chiral separation, so they're inherently a little less efficient. So the question is, can we have new particle technologies, or new column technologies that can help relieve this problem of slow adsorption-desorption kinetics? And that's what we'll talk about the rest of this presentation. Now, the first really highly efficient chiral separation by HPLC using a high-efficiency HPLC column was in fact performed on an achiral HPLC column. This was done on the separation of 4 beta blockers, which are shown on this slide, in 2010. And in fact, the way the separation was performed was the enantiomeric beta blockers were derivatized with a chiral agent, making them diastereomers, which could then be separated on an achiral high-efficiency UHPLC C18 column. So in fact, it is a diastereomeric separation, but it is the first report of doing chiral-type separations in a UHPLC configuration. Now, a few years later, in 2013, Hammond et al. At Genentech experimented with high-efficiency sub-2 micron chiral columns, which were actually coated with chiral selectors. These, in this situation shown on this slide, we were coated with an amylose-based chiral selector, and the researchers did a comparison between 3 micron, which you can see a chromatogram on the top on this slide, compared to a 1.7 micron-based column. And this is an SFC separation of transdilbene oxide. And what the researchers found was that the 1.7 micron coated chiral stationary phase only gave about half the separations as did the 3 micron material. And you can see in the comparison of the transdilbene oxide that indeed the efficiency is quite good on the 1.7 micron phase, but the selectivity is drastically lowered, and so is the resolution. So overall, the number of separations that were obtained on this high efficiency column were actually fewer. Now, simultaneously, researchers in Italy started studying pi complex-based chiral selectors and bonding them to sub-2 micron fully porous particles. Now remember, pi complex-based brush-type chiral selectors are much smaller than the polysaccharide-type chiral selectors that I described on the previous slide. Now the results are shown here. This is again a pi complex brush type chiral selector bonded to sub 2 micron silica. And you can see in the chromatogram in the upper left corner we have a separation done in 120 seconds. Now be mindful that a lot of the axes I'll show in this talk will be in seconds and not in minutes because we're talking about high speed separations. So we have a separation in about 120 seconds or 2 minutes with a resolution of 2.5, which is quite good. And what they showed is that they could increase the flow rate as they go around this circle in this diagram and get much faster separations. In the last one you see 4.5 milliliters per minute. We have a resolution of about 1.9 in 30 seconds. So this was the first example of an ultra-fast chiral HPLC separation. And by ultra-fast chiral HPLC separation I mean it was ultra-fast in the fact that it occurred in less than 60 seconds. So I'll refer to this technology a lot throughout my talk, but ultra-fast simply means that the separation occurred in less than 60 seconds. And what they pointed out was that with these small particles, they're able to go to higher flow rates and get comparable resolutions, but their speed is increased quite a bit. In this case, resolution only decreased 30%, but the speed increased by 3 times. This slide simply shows an extension of the work done by Villani and coworkers. In this case, they used a different pi complex type brush type chiral selector. In this slide, I've shown 4 examples of some ultra-fast chiral separations. Again, these separations are done in seconds, 10 to 15 seconds on this slide. In this case, the chiral selector, which was bonded to 1.7 micron fully porous particles, was the Welco chiral selector. Recently, the idea of UHPLC chiral columns was furthered through the use of narrow particle size distribution, or so-called monodispersed silica. And what I've shown on this slide is just an overview of what monodispersed or narrow particle size distribution sub 2 micron fully porous particles are. If we look at the top 3 pictures, you see SEM images of some sub 2 micron particles, fully porous particles. On the left, we have a 1.9 micron narrow particle size distribution particle, also called monodispersed particles. And on the right, you can see your more common and traditional 1.7 and 1.8 micron UHPLC particles. And on the bottom, we see a plot comparing the particle size distribution of these different particles. And what you can see from the plot and from the pictures is that the particle size distribution for these monodispersed particles is much more narrow. In fact, the relative standard deviation of the particle size distribution for the monodispersed particles is about 10%, whereas your traditional UHPLC particles is about 25%. So what happens is when you pack columns that have monodispersed particles, they pack more evenly across the column, and you get a more efficiently packed column, and of course that gives you higher resolution separations. Such narrow particle size distribution particles have been functionalized with chiral selectors, and I've shown an example of that on this slide. On this slide, we're looking at the use of macrocyclic glycopeptide chiral selectors as they've been bonded to monodispersed silica. Here we have a comparison on the left in A for teichoplanin-based chiral phases, both on a 5 micron in the red chromatogram in A and 1.9 micron monodispersed silica in the blue chromatogram on A. That's using teichoplanin as the chiral stationary phase. And in B, we have the vancomycin chiral selector on 5 micron silica in the red chromatogram, and the vancomycin chiral selector on the monodispersed 1.9 micron silica in the blue chromatogram. And what you can see is quite clear that in both cases, the efficiency increased about 2 to 4 times using the monodispersed silica, and the resolution approximately doubled. And another nice thing to point out is that when this technology was converted to the commercially available 5 micron technology to this new monodispersed sub 2 micron technologies, that the selectivity stayed approximately the same, and so did the retention times. So this technology could be useful for screening, and if you wanted to develop a prep method from your screening method, you could go directly from your sub 2 micron fully porous particle column up to a smaller particle, fully porous particle column, and have about the same separation, and easily transfer to a prep separation. Now, I won't go into any detail on this slide in the interest of time. I just wanted to show that these monodispersed and these sub 2 micron based fully porous particle chiral station phases can be used to perform ultrafast separations. In this slide, the top 3 chromatograms show some ultrafast separations using the monodispersed silica with a teichoplanin based chiral selector. And on the bottom, we have 2 chromatograms using the vancomycin-based chiral selector on the monodispersed silica, and separations happening in anywhere from 30 to 60 seconds. And there's one more example on the bottom right where teichoplanin A glycon was bonded to the 1.9 micron monodispersed silica, again showing very highly efficient and very high speed chiral separations. Now I'm going to discuss another route towards high-efficiency chiral stationary phases. First, I discussed UHPLC silica and sub-2 micron particles and how they could be used to give rather fast and rather efficient separations. Well, there's another option other than using small particles, and that is to use superficially porous particles. So what about SPPs, or superficially porous particles? How can they be used in chiral stationary phases? Well, of course, SPPs were actually conceived in the 60s by Horvath, but they were later not really commercially available in the particle technologies that we know in terms of superficially porous particles until about 2007. And since that time, they've made a big impact, and I'm sure that many of you who do achiral separations are currently using superficially porous particle-based columns. Of course, SPPs have an inert solid core, which is a monodispersed non-porous core, which is typically around 1.7 microns. And surrounding that non-porous core is the porous region of silica, which is typically around half a micron thick. Now, when you do the geometry and you calculate it out, when you take this superficially porous particle and compare it to a fully porous particle of the same size, you get about 75% of the porosity retained. So you do lose some surface area, but you retain quite a bit. One thing that is hugely important when it comes to superficially porous particles is that their efficiencies often match the efficiencies of sub-2 micron particles, even though they're 2.7 micron in diameter, but they have much greater permeability. So you can get the same efficiency on an SPP-based column with 2.7 microns when you compare that to a sub-2 micron-based column, which is going to have much lower permeability because of the small particle size. And lastly, you will see lower retention and slightly lower loadability on SPP-based columns, and that's because the porosity decreased because of the solid core. So you'll have overall less surface area, which will give you less retention on an SPP-based column. But alas, this is not a big problem because we are looking at speeding up our chiral separation, so it actually can be helpful in this situation. Just in general, superficially porous particles also have excellent efficiency, and the reason they have excellent efficiency is they can decrease all contributions to band broadening. First, SPPs can decrease longitudinal diffusion because of the obstruction of the solid core. So if you considered stopping the flow of your HPLC experiment while your band was right in the middle of the column, and considered it diffusing outwards towards both inlet and outlet of the column, you can see that the band would actually be obstructed by the presence of the solid core. So we have a decrease in longitudinal diffusion because of the obstruction factor of the solid core. Second, eddy dispersion is decreased due to the packing homogeneity. Because of the particle morphology involved in superficially porous particles, they generally pack very, very well in HPLC columns, and this gives very low eddy dispersion effects. And lastly, mass transfer effects for very large molecules with low diffusion coefficients, or molecules with slow adsorption-desorption kinetics like we have in chiral separations, can be decreased quite a bit using superficially porous particles. So on this slide, I've shown the first attempt at using superficially porous particles to produce a chiral stationary phase. And in this research, a coated polysaccharide chiral selector was used to coat superficially porous particles and compared to a 5 micron fully porous particle chiral stationary phase coated with the same chiral selector. And what the researchers reported were different chiral selector loadings, and they saw some decrease in enantiomeric selectivities. You can see in the chromatograms below that the fully porous silica had, this is the alpha FPP, had an alpha of 2.85, whereas the superficially porous particles had an alpha of 2.47. So we had decreased selectivities. And in addition, you can see the efficiencies on the fully porous particle around 16,000 plates, and on the superficially porous particle also around 16,000 plates. So not a huge gain reported here, but it was the first attempt at using SPPs for producing chiral stationary phases. Most recently, there was a very recent report in August of using coated polysaccharides on SPPs to make new chiral stationary phases again. And what can be seen here in these chromatograms is that there are a few examples of high efficiency. The first chromatogram has about 130,000 plates per meter for the first peak, which is highly efficient for a chiral separation. But you see some of the other separations are as low as 30,000 plates per meter. So maybe not a big gain there in separations. And you can see that even in chromatogram A, where the efficiency was quite high, there is some major tailing going on and some peak shape issues. So perhaps at this point in time, large polymer-based columns might not be suitable, or large polymer-based chiral selectors might not be fully suitable for SPP-based chiral stationary phases. But the question is, what about the brush-type chiral selectors that we've discussed a little bit already? Well, if we look at this slide, we see the very first successful SPP-based chiral stationary phase, which was produced with a brush-type chiral selector. In this case, it was a cyclofructan-based chiral selector, which is a cyclic oligosaccharide, and it was bonded to superficially porous particles. And on this slide, you can see, using the same mobile phase, the researchers compared 5-micron fully porous particles in red, 3-micron fully porous particles in black, 2-micron fully porous particles in blue, and 2.7-micron superficially porous particles in green. And what you can see is that the highest efficiency comes from the superficially porous particles, as shown in green. And when compared to the state-of-the-art, which is the 5-micron fully porous particles shown in red, you can see that the efficiency is more than doubled than the current state-of-the-art. Finally, you can see that the resolution has greatly increased from the 5-micron. But you might see that the 2.1-micron fully porous particle actually gave the highest resolution. And that's true. In this case, it did give a higher resolution than the superficially porous particle. But two other things to point out there in that comparison between the blue chromatogram and the green chromatogram is that using the 2-micron fully porous particles, although with higher resolution, the back pressure is slightly higher, and the analysis time is about twice as long when compared to the superficially porous particle. And that again is due to the decreased surface area on superficially porous particles, resulting in faster analysis times. So let's take a look at what happens when you do the same exact comparison which was shown on the previous slide, but switch the mobile phase such that all the peaks come out in about the same time. So this is generally referred to as a constant analysis comparison between chiral columns. So we have, again, the 5-micron fully porous, 3-micron fully porous, 2-micron fully porous, and the 2.7 superficially porous on the bottom. And now you can see under constant analysis time conditions, you can see that the superficially porous particle column indeed is the most successful column in separating this chiral atrope isomer binam. Again, that was the first use of a brush-type chiral selector to make a chiral stationary phase successfully and with high efficiency from superficially porous particles. This research was furthered by looking at several other brush-type chiral selectors, and it is ongoing. On the top section of this table, you can see some that were reported recently. The top two, 1 and 2, in the top portion of the table are cyclofructan-based chiral selectors, which had efficiencies around 200,000 plates per meter. 3, 4, and 5 are macrocyclic glycopeptide-based chiral selectors, and they had efficiencies ranging from 130 to 170,000 plates per meter. And lastly, there was a cyclodextrin-based SPP phase produced, which had about 180,000 plates per meter. And all these plates can be compared to 5-micron state-of-the-art fully porous particle-based columns, and in general, they're 3 to 4 times higher. So indeed, it does look that brush-type chiral selectors can be bonded to superficially porous particles to greatly increase the efficiency of those chiral stationary phases. Now, one other thing that has been reported when looking at superficially porous particles is that when they're used at higher flow rates, their separations do not diminish very much. And that's what's described in these Van Dempter curves shown on this slide. We have 3 Van Dempter curves, column 1, column 2, and column 3. Column 1 is a 5-micron fully porous particle-based cyclofructan phase. Column 2 is a 3-micron cyclofructan phase, and column 3 is the superficially porous particle cyclofructan phase. And what you can see, and the main point, is that the slope of the Van Dempter curve for the superficially porous particle-based column is very minimal. It's almost a flat Van Dempter curve when you go to higher flow rates, whereas the fully porous particle-based columns are going much, much higher, and the efficiency is decreasing dramatically as you increase the efficiency. This indicates the fact that these particles can also be used for ultrafast chiral separations. And I've shown a few examples of such ultrafast chiral separations using SPP-based chiral stationary phases here. These are just 6 examples showing different superficially porous particle-based chiral phases, and I've indicated the chiral selector next to each chromatogram. Some are cyclodextrin, some are macrocyclic glycopeptides, some are cyclofructan-based, and you see we have different separations. We have chiral drugs such as thalidomide, chiral catalysts such as Jacobson's catalyst. We also have a dipeptide separated, shown on the teicoplanin's SPP phase. That separation separated 4 stereoisomers in 40 seconds. All the other separations are around 10 to 15 seconds. And you can see thalidomide was separated in about 5 seconds using the new SPP-based chiral stationary phases. I should mention at this point that some of these separations, particularly those that are occurring in less than 10 seconds, are actually happening much faster than we can even inject the samples. The typical autosampler takes anywhere from 30 seconds to a minute to inject a sample, and some of these separations are occurring in a third of that time. So really, the rate-limiting step on some of the separations is now the instrumentation. Now we've moved on to our second polling question, so I'll pass the mic over to Laura so that she can handle the polling question.
Thanks, Zach. Once again, for all of you in the audience, you can click directly on your screen to answer. And so as you can see, the question is, what type of chiral column do you prefer? Cellulose, amylose, Perkel type, or other? Once again, click directly on your screen to answer. What type of chiral column do you prefer? Cellulose, amylose, Perkel type, or other? All right, just to keep things moving, let's bring the results up. Okay, we've got kind of a range there, but with the cellulose and amylose definitely being the most popular. All right, thanks so much, everybody, for taking the poll. Zach, back to you.
Sure, and I'm just going to get into some interesting idiosyncrasies that deal with these fast chiral separations, but I was interested in the poll results, so I'll just briefly comment on that. A lot of the technologies that I'm discussing and are coming out recently with the new particle technologies, whether it be the sub-2 micron or the SPP-based, seem to be focused on the brush-type chiral selectors. And that's just because they're a little easier to work with and bond to some of these new particle technologies. That doesn't mean that these polysaccharide-based phases won't be, at some point, amenable to these column technologies. But at the moment, it might be useful for some of these new technologies to be used in secondary or parallel screening units in the proper modes, whether it be polar organic or reverse phase, to complement the existing polysaccharide-based separations that may be happening in your labs today. That's an excellent polling question. Okay, so back to some of the stuff I was talking with, the ultra-fast separations. As I mentioned just before the polling question, there are a few things that we should be concerned with when doing some of these ultra-fast and high-efficiency separations. Just a few idiosyncrasies that we should be mindful of, and I'll mention a couple of them on the next few slides. First, one consideration that should be taken is frictional heating. When doing some of these ultra-fast separations, we're frequently using very high flow rates, 5 milliliters, 6 milliliters per minute, doing your separations on a 4.6 ID column. And when you flow that fast through a column with smaller particles, you get frictional heating from the mobile phase rubbing across these rough particles. And when you get heating, you have some interesting things that can happen. And I've shown one interesting outcome, which is possible when doing high-speed separations. And this is shown on these Van Dempter curves on this slide. So what I show here is the separation of D and L homophenylalanine along with an achiral marker 1,3-dinitrobenzene. These are Van Dempter curves, so we varied the flow rate and measured the efficiencies, or the plate height on the y-axis. So it was done on the reverse phase in a teicoplanin-based SPP column, and we went the flow rate all the way up to 3 mils per minute. And what you see, and we'll just maybe look at D-homophenylalanine, the green curve. This is the most retained enantiomer on this chiral separation, and what you see is it doesn't look like a normal Van Dempter curve, or the Van Dempter curves I showed you earlier, where you had a curve which starts low at low flow rates and goes high at higher flow rates. We actually see that at high flow rates, the plate height starts to decrease. That means the efficiency is actually increasing at high flow rates. This is pretty interesting. So what it turns out is what's happening here is that as you go to higher and higher flow rate, the column essentially heats up down the length of the column and increases the rate at which the analytes can adsorb and desorb from the chiral stationary phase, giving you higher efficiency. So at higher flow rates, if you get frictional heating, you actually may see increases in efficiency, which is pretty unique. It's very unique Van Dempter curves, as you can see here. Now, it's not really an excellent way to go about developing a method to go to higher flow rates and get higher efficiency, because the other side of that is when you go to higher temperatures from this frictional heating effect, you'll actually decrease your selectivity because most chiral separations are enthalpically driven. So typically your separations will still be worse, slightly worse at the higher flow rate. On this slide, I've shown another thing to consider when using high-efficiency chiral HPLC columns and doing high-speed HPLC chiral separations. On this slide, I've shown separation of binam, an axial chiral compound, is shown to the left, and I've shown the injection of that compound on a cyclofructan-based SPP column in about 6 different chromatograms. In each of these chromatograms, the sample is the same, the column is the same, the mobile phase is the same. It was the same day, just injected in sequence. The only difference is that the detector settings and the sampling rate of the detector was increased as we go from the red all the way up to the green chromatogram. And what you can see is if you have the proper settings on your instrument, you can actually realize the intrinsic separation capabilities of your column. So in all cases, the column is able to separate this compound baseline, but if you have the inappropriate settings on your detector, you may see a separation such as the red and the purple separation. So just something to be mindful. Of course, if you have longer separations, it's not as big of an issue, or if you have less efficient separations, it's not as big of an issue. But if you're doing highly efficient separations, which is capable of doing on some of the new technologies, then it's important to make sure that your system is suitable. Now, what about SFC? SFC, of course, is seeing great usefulness in chiral separations. There's many advantages. It's cheaper, it's complementary, it can do most normal phase separations, you can go to higher flow rates, the column equilibration is fast. For all these reasons, SFC is becoming hugely important in chiral separations, and oftentimes when doing chiral separation screening, SFC is employed. So the question is, can these new high-efficiency chiral columns also give equivalent improvements in SFC? And the short answer is yes. I won't go into a lot of detail for SFC on these high-efficiency columns, but just to tell you, yes, you can get the same improvements you get in HPLC. So what we see here on an SPP-based chiral column is on the left we have HPLC separations of derivatized amino acid. On the bottom you have 5 micron compared to the 2.7 SPP column on top, and you can see that you can use about 1/3 of the length of the column and get about the same resolution in approximately 1/3 of the time, or less. And if you go over to the SFC chromatograms on the right, you see you get the same chromatograms going from fully porous particles to superficially porous particles. So you can easily transfer from one HPLC to the SFC method or vice versa. And on this slide, we have just a few SFC separations using the sub-2 micron fully porous particles. The previous slide showed the capability of the SPP-based particles. Here's the sub-2 micron. One thing that I should point out is if you're doing SFC, sub-2 micron might be a little bit more attractive to you because you don't have the back pressure issues that you do in HPLC. So, of course, using a 2.7 micron SPP-based chiral phase has the advantage of greater permeability. Whereas if you go to SFC, permeability is now no longer an issue, and sub-2 micron FPPs might be an excellent choice. Now, one more consideration that should be made for high-efficiency separations is the effect of extra column in your system and how the extra column volume can affect your separations. So let's disregard the table on the right and just look at the chromatograms on the left, which is the effect of decreasing extra column volume in UHPLC chiral separations. This is a similar set of chromatograms that I showed earlier with the detector response. We're separating binam, but in this case we've gone from a stock UHPLC condition, a new UHPLC was delivered, and just simply decreased the extra column volume by making use of smaller tubing IDs, smaller injector seats, and the volume of the detector flow cell. What you can see is if you decrease your extra column effects, you greatly increase your efficiency from 2,500 plates all the way up to above 3,000 plates for the optimized system. So again, it's important to make sure your system is suitable. In HPLC, generally, the smaller the volume, the better off you'll be. Now, I do want to point out that that's not always the case when doing SFC. If you look to the right, you can see an example where researchers decreased their tubing ID from 254 microns down all the way to 75 microns. And when they decreased that volume, when they expected to see the efficiency increase, you actually had efficiency decrease. That's because in SFC the mobile phase is compressible, and the more compressed it gets because of the smaller tubing, think of a hose getting smaller and squeezed, the mobile phase gets more compressed and the diffusivity of the analyte in the mobile phase decreases, and eventually you get an actual decrease in efficiency. So in SFC, there's some different rules to play by, but just have to be mindful. Of course, you can't go enormous on your tubing ID, but you should find the proper setting for your system. Now the last few slides will just talk about what can we do next, where are we going to go next, and how can we go further. This slide just shows a couple things that can be done to go even faster and more efficient in chiral separations. In A, you can see a chiral column, which is 1/2 centimeter in length. If you remember doing chiral separations 5 years ago, you used a 25 centimeter column with 4.6 ID. Now you can see what a new chiral column on the horizon looks like, 1/2 centimeter in length. With these small chiral columns, you can screw them right into your detector, which is shown in B, and you can have an injector that's very close to your column, and you can do very, very fast separations. And with those types of system settings, you can actually do, and this is the first example of it being done in HPLC, sub-second chiral separation. So here's your first ever reported sub-second chiral HPLC packed column separation. Here's separation of DL, DNB leucine. And these columns can also be used for other achiral separations. Here's a sub-second. Again, this is 0.89 seconds for this separation to occur in a HILIC separation. Separation of amino acids. And finally, another separation of amino acids where you have a single amino acid polymorphism where you have just one amino acid in this dipeptide change. Again, the separation occurring in just under 1 second. And that was all done on SPP-based columns, and very recently, just this month, a paper was published showing that sub-2 micron silica can also be used to produce sub-second chiral separations. And in that paper, there's a little more detail, but I think I'll skip this last slide in the interest of time and just go to the conclusion. So what we've seen here in the talk is that brush-type chiral phases have been effectively bonded to SPP and sub-2 micron fully porous particles and made very highly efficient chiral stationary phases, which I believe are going to be quite impactful to the end user in the coming years. We saw that the resulting columns produced faster, more efficient separations, and we saw ultrafast separations can be done, and even sub-second separations are now possible, which might not be used by everybody, but when you think about the potential for two-dimensional chiral separations where you have, say, an achiral column and you're comprehensively injecting peaks into a second dimension, you might need very, very fast separations. All this amounts to the fact that chiral screening can be even faster. So finding that chiral column or that chiral method can be a little bit quicker for the end user. And finally, future enantiomeric separations do not have to be inefficient. We can see now that some of the chiral separations that are being reported in the literature and will someday soon be available to the end user is that chiral separations may be just as efficient as some of the achiral separations that you're performing. And with that, that wraps up my portion of the talk, so I thank everybody for their attention, and I think there's another polling question, so I can pass it back to Laura.
Thank you very much, Zach, for that excellent presentation. And yes, for all of you in the audience, we have one last quick polling question before we go to Q&A. So it's on your screen, and you can click directly on your screen to answer. Which technology do you see most impacting the future of chiral column chromatography? Small particle silica, multidimensionals, new CSPs, or new selectivity? So once again, which technology do you see most impacting the future of chiral column chromatography? Small particle silica, multidimensionals, new chiral stationary phases, or new selectivity? All right, let's pull that up, the results. Okay, it's fairly split here, but the biggest majority is definitely the new chiral stationary phases and new selectivity, but with some faith in small particle silica and multidimensionals as well. Fantastic. Okay, so let's move to our Q&A. As a reminder, if you want to submit a question, just type it in the Q&A box, which you can find on the right-hand side of your screen. All right, first question, Zach. In the long run, so this kind of relates to the question we just talked about, what do you think? Which new technology will win out, SPP-based CSPs or sub-2 micron-based CSPs?
That is a good question, and the short answer was I would think that the jury may still be out. I think that was obvious in the answers we got on the polling question. That was kind of split between SPPs and small particles, and I was really interested to see that the new selective chiral selectors got the highest percent, because that area of research is the best way to increase your ability to separate enantiomers is to have a selective phase, but that area of research has been covered for 20 years, and there's so many phases out there available. So, that being said, back to the question, depending on the user's needs and the application, I think that's really going to be a toss-up whether or not SPP-based chiral phases will be more useful, or will the sub-2 micron phase be more useful. Say you only have a 400 bar instrument and you want to transfer a robust chiral method all around the world, maybe an SPP-based column is more useful because it's more amenable to the system you have in your lab. Now, if you're doing SFC, where back pressure is not an issue, or you want to transfer your method to prep methods, perhaps sub-2 micron chiral stationary phases are useful. So, again, I think time will tell. Both of these technologies, I believe, will be available in the very near future, and time will tell.
Thanks, Zach. Here's another one. Why do chiral HPLC separations tend to tail more than achiral separations?
That's an excellent question. I think it relates back to the slow adsorption-desorption kinetics you often find in chiral separations. So in chiral separations, you need 3 points of interaction, not necessarily attraction, but interaction. But in most cases, there's often a strong interaction, exceptionally for the second eluting enantiomer. So you can think of this second enantiomer that really locks in like a locking key with your chiral stationary phase. And it's hard and more difficult to get off the stationary phase as the mobile phase tries to push it out of the column. So because of these stronger interactions, which are often required to actually realize a nice chiral separation, you can frequently see more tailing in chiral separations. But I think some of this is going to be circumvented by some of the new technologies. Of course, with SPP-based columns and sub-2 micron columns, you often have faster absorption-desorption kinetics, and you're going to allow yourself the ability to have higher efficiency chiral separations.
Excellent. Thank you. Can you briefly explain the parameters affecting retention in polar organic mode?
Yes, polar organic mode. Now that's going to depend which chiral selector you're using. Just for general knowledge out there, polar organic mode is typically acetonitrile methanol mixtures with some additives. So if you're using a cyclodextrin phase, you're typically going to be using polar organic mode with, say, 90% or more of acetonitrile and a small amount of methanol, typically with some additives. In a cyclofructan phase, polar organic mode might be 70% acetonitrile with methanol. So it really depends on which column you're using. Of course, in the macrocyclic glycopeptides, they have different prescribed polar organic mode mobile phases too. And this brings up a good point. When doing any chiral separation, you should look at what the vendor suggests you use. What might be a good mobile phase for a polysaccharide column might be a bad mobile phase to test on a macrocyclic glycopeptide column, even though both columns are capable of performing a separation. So that's very important. Now, when looking at the polar organic separations, you really want to start with something strong, say 40% methanol, see your peaks. Usually, you're going to use additives because when you're doing polar organic separations, you frequently have a polar analyte. So typically, people will use a little bit of acetic acid mixed with triethylamine. And those ratios of the acid and base can be varied to help your efficiency. So look at your ratio of methanol acetonitrile to get retention, which you like, and see selectivity. Then use your acid-base ratios to realize the resolution you need by increasing your efficiencies.
Excellent. Thank you. There's a question about slide 24. Maybe we could bring that up. If you want, I can do that. It says, it's a little unclear to me what the question is, but maybe you can understand it.
Sure.
Why is the pressure of SPP column pressure about pressure if 1.8 micrometer fully FFP column? Can you follow that?
No, this may be from, is this from this slide or maybe 23?
Oh, I'm sorry. It was, oh, maybe it's 23.
Let's go to 23 because I think this might relate to the question. I have a bullet point here that says that, well, it should say that the pressure, the permeability is about the same as a fully porous particle. So the question, I'm not sure. It could be two things. One could be, why is the pressure of a fully porous particle, UHPLC particle column, higher than that for SPP. That's an easy one to answer. So as the particle size decreases, the back pressure goes up. The smaller the particle is that you pack into your column, the higher the back pressure is. So if you're going to use the UHPLC-based chiral phases, you may need a 600 bar instrument or a UHPLC instrument. Now, the question could also be relating to, does the fully porous particle of the same diameter of a superficially porous particle have the same permeability? And why do I make that statement? Well, that's a more difficult question to answer. And really, the reason that they turn out to be pretty approximate is because you do have this core in the superficially porous particle, so that's going to block your flow. So one would say this should increase your pressure. But because of the way that superficially porous particles pack across the bed of an HPLC column, they're actually slightly more permeable. So there's a balancing act between the packing density in an SPP column and the density of the core of the particle, which generally comes out to similar permeability to a fully porous particle of the same outer diameter.
Fantastic. We now have a question about slide 12, if you want to bring that up.
Sure.
And the question is, what is the source of tailing in slide 12? I think there are multiple.
Okay. Slide 12. Maybe my, oh, okay. I'm on.
Yeah, maybe it's not exactly 12.
And 12 here. Okay, there we go. So
yeah,
the separation of trans-stilbene, yeah, that's fine. Trans-stilbene oxide. The separation question is about the 3 micron column. We have poor tailing on that top chromatogram. This is apparently an issue with that column. It looks like the column is probably damaged. You might have an issue with the packed bed. I think in that case, that is not indicative of the way that column is supposed to behave. I don't think this is a chemical interaction. I think there's an issue with that researcher's column.
Thank you.
Yes.
Can we predict the best column to separate enantiomers using the chemical structure of the analyte?
That's a great question. Actually, at the Chiral conference in Germany in July, there was a presentation from Chris Welch at Merck discussing the potential for doing this. The answer is no, we're not there yet. But the answer is, I think, several years out in the future, that there will be knowledge-based software which will allow us to do that. It's a matter of building a library with as many separations and as many structures that can be known, and getting into the library. And then you plug in your structure, and then a knowledge-based software can use qualitative structural relationships to give you your best bet on a phase. I think that is something that's going to come, not in the near future, but certainly sometime. I think that is possible. It won't be foolproof. I don't think that's possible. But I think that is coming. So look for papers coming out which describe QSAR types of method development for chiral separations, and I think that there is research ongoing with that.
Fantastic. Let's just take a couple more here as we're getting close to the top of the hour. This viewer says, I need to separate a diastereomer by UHPLC. Which column type do you suggest I start with?
Well, that's an excellent question. If it's a diastereomer and you're using UHPLC, I would personally probably start just with an achiral column and look at just your typical core shell C18, core shell C8, and core shell PFP. If those don't work, then maybe escalate it to a chiral phase. Chiral phases have that extra ability to be selective, but we do lots of diastereomeric separations on our achiral columns here every day. So I would start with the easy thing and then go to the next. The next level answer is, when you get to that level and you need to use a chiral phase to try, it really depends on the structure. If it's something that's normal phase soluble and you're okay with a normal phase separation, maybe try a polar organic. But if you want to do reverse phase, because most method developments for diastereomers are in reverse phase, a cyclodextrin column is actually a great column for diastereomeric and structural isomer separations that are not necessarily enantiomers, and that's been described for the last 20 or 30 years. So, hydroxypropyl cyclodextrin might be an excellent thing to try.
Excellent. A lot of the new column technology research appears to be focusing on the brush-type chiral selectors, but I typically use polysaccharide-based columns. Where will the new columns fit in with my current screening protocols?
That's a good question, and I tried to address that earlier after that polling question because, of course, polysaccharides are so selective and so user-friendly. So the problem is right now the technology of the new particles merging with the polysaccharides is not quite there. But I should note that some of the brush-type chiral selectors, such as glycopeptides, have similar selectivity to polysaccharides if they're used in the prescribed modes, such as polar organic or reverse phase. So where I see it going right now is that researchers will have their setup with the polysaccharides, separations on column switching, like they have right now, but maybe they want to bring in a side-by-side screener or a secondary screener, which is going to be based on some of these brush-type phases, which may be more useful in liquid chromatography, in polar organic mode or reverse phase mode. And also keep in mind, if the analyte or the matrix is very polar, that SFC is not going to be useful, and some of these more polar brush-type chiral selectors are going to be the best choices for separations. And finally, if we see a growth of two-dimensional separations, for example, we had done a separation where we had a reverse phase separation, pulling amino acids away from each other and then cutting that into a chiral column to separate the enantiomers and get the enantiomeric ratio from a biological sample for amino acids. You can see in that situation it's good to have a reverse phase type chiral selector, which is some of these brush type chiral selectors in the second dimension. So I think as secondary screeners and some of these more polar analytes and some of these more difficult biologics and biological samples come out, these columns will be highly impactful.
Fantastic. Well, Zach, thank you so much for your excellent presentation and for answering all those questions today.
You're welcome.
And I'd like to thank all of you in the audience for watching today and for participating, particularly in our polling questions. And I'd like to thank our sponsor, Regis Technologies, for making today's webcast possible. Today's webcast will be available for on-demand viewing through September of next year. You'll receive an email soon from LCGC alerting you when the webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.